Kielak, and he's going to talk about universal L2-torsion for free-by-cyclic.
Thank you. Thank you for having me. So I wanted to start by a quick discussion of three manifolds. In particular, hyperbolic ones. So my manifolds will be closed, connected and oriented. Okay, so we want to talk about three manifolds. So I guess the first question that comes to mind is how do I make a three manifold? So here's a method. You start with a surface, closed surface of genus at least 2, okay? So that's the surface. And now I take a homeomorphism F, orientation preserving, and we're going to construct the mapping torus. So we take, we take a product of our surface with an interval, and we glue the top to the bottom by F, right? So on the level of fundamental, I should say, so this manifold M, so we obtain a manifold M by taking this torus, identifying point, 0 with F of this point, 1. And this manifold M is hyperbolic if and only if F is a pseudo-Anosov mapping class. So if you don't know what pseudo-Anosov means, then this is the definition. If you do know, this is a theorem. So now I will mention the fantastic result of Ian Agel, based, I guess, on the work of Danny Weiss, which says that every hyperbolic, closed hyperbolic three manifold admits a finite cover which is phi bet, and phi bet is defined exactly by this construction. Okay, so phi bet means that you can obtain it like this. Okay, so what does it all mean on the level of fundamental groups? So on the level of groups, you see that you have your, well, we are thinking about a phi bet manifold. You take your phi bet 3 manifold M, you can map its fundamental group onto the fundamental group of S1, which is Z, and here you have the fundamental group of the surface over which we are fibering, right? And this is an exact sequence. This is exact. Okay, so that means that we can write the fundamental group of our three manifold as the surface group and the stable letter, and we have relations, and the relations are that if you take any loop, any element in the fundamental group of sigma, hit it with the stable letter, you are going to get f of x. Okay, so it all makes sense because x is an element of the fundamental group, so it's a loop. We hit a loop with a homeomorphism, we get a loop, so it's all fine, right? Except, of course, not, because this only gives you a well-defined conjugacy class, not a well-defined element, but we don't have to worry. Okay, it's a fact that if you take any automorphism of the fundamental group and you change it by the conjugation, then in fact you get the same group here. Okay, so we don't worry about that. All right, so now I wanted to go into the Thurston norm. No, some facts first. So, and the definition. Sorry. Okay, so first the definition. So if we take a group H, then any group G, if we write H star F of this form, so H and the stable letter and the relations of this form is an ascending H and N extension, provided that F is a monomorphism from H to H. Okay, so this is a definition of a ascending H&N extension. In particular, here's a bunch of facts. Okay, so, well, the first fact is that any semi-direct product is an ascending H&N extension. Right, this is a particular case because an automorphism is, of course, a monomorphism. All right, now another definition. So, if I have an ascending H&N extension, then I can define a map to Z. That's an epimorphism to Z in the following way. Everything in H is going to be sent to 0, and T, the stable letter of the H&N extension, is going to go to the generator 1. Okay, so this guy is called phi, and phi is the character induced by the ascending H&N extension. Okay. So, right, Thurston norm. So here's another definition. Right. So we take our 3 manifold and we take a character phi from the fundamental group of the 3 manifold onto Z. So such a morphism is, of course, an element of the first cohomology of the manifold. I mean, this is, after all, the definition of the first cohomology. And to this guy, we are going to associate a number. Okay, so this number is going to be the Thurston norm. This is how we define it. So what do we start with? So we have an element of the first cohomology of the 3 manifold. Poincaré duality tells you that an element of first cohomology is dual to an element of the second homology, right? Now, it so turns out that in 3 manifolds, elements of second homology are represented by embedded surfaces. Yeah, this is an exercise. So we are going to look at surfaces embedded in our 3 manifold, dual to the cohomology to the character phi. Okay, sorry, I should say this is what we, yeah. Okay, and now for each such surface, so I should stress, these are not necessarily connected. Yeah, that's important. So to each such surface, we are going to associate a number, which is called chi minus. Okay, and once we do that, we take the minimum over all the surfaces. Okay, so I have to tell you what chi minus is to complete the definition. So what is chi minus? Well, chi minus is the sum over connected components, let's say I, in, let's say 1 maybe, in the pi naught of sigma, and it essentially calculates minus Euler characteristic, except you want to throw away spheres. So we take maximum between 0 and minus Euler characteristic of sigma 1. Okay, so again, you start with a character with a cohomology class. You look at all possible surfaces dual to it. Each such surface you break into bits, into connected components. You throw away the spheres for the other guys. You take minus the Euler characteristic, sum it all, and altogether take a minimum of this. Okay? So Thurston norm looks for the least complicated surface dual to a cohomology class. That's the idea. Okay, now I need to clean the boards, it seems. Right. So the definition is due to Thurston, and Thurston also proved a number of facts about it. So as I wrote it, the only thing which is clear is that this is a non-negative number, right? But so first of all, okay, so here are facts. Theorem Thurston. So the first thing you do is we define this Thurston norm only on integral cohomology classes, and we want to define them on real cohomology classes. So the first bullet point is that you can actually extend to the first cohomology of the manifold with real coefficients. And this is just by continuity. Now, what we also know, and this is justification for the name, is that the Thurston norm is really a semi-norm. Okay, it's a semi-norm. And in fact, if M is hyperbolic, then it is actually a norm. Okay. Now, the unit ball. So if you have a norm or a semi-norm, you can study its unit ball. So the unit ball of the Thurston norm in H upper 1 M R is a finite-sided polytope. Okay. Right. And now here's another interesting fact. So a character, so there exists a finite collection of maximal open faces in the unit ball such that a character, say Z, is fibered, meaning that M is fibered, and the fibration, when you write it in terms of H and N extensions, induces this very character. So phi is fibered if and only if it lies in the cone, the positive cone, well, it doesn't matter actually in this case, in the cone over one of these maximal faces. All right, so there's a picture for this. The picture is the following. So the unit ball is going to be some polytope, maybe like that. This is where the origin lies. And now there's some number of maximal open faces. So maximal faces are edges. So we would pick some open edges, maybe these. We take a cone. And this is precisely where the fibered cohomology classes lie. So these guys are called fibered faces. Okay, so one more fact, one more bullet point, is that if phi is fibered character, then the Thurston norm and fibered with fiber sigma, then the Thurston norm of phi actually is the Euler characteristic of sigma. Okay, so for a fiber character, it detects really over Watt fiber. All right. Okay, so So this was that about 3 manifolds, and now we move into the L2 setting. So all I'm going to talk about now is due to Friedl and Lück, and this works in a large generality for groups which satisfy the following. So our G is going to be a G admits finite cellular KG1, which I will call X. G is L2-acyclic. G satisfies the Atiyah conjecture, and G has trivial Whitehead group. Okay, so all of this will be gold star. Okay, so this is a bunch of conditions. If you don't know what they mean, don't worry. I will explain the ones which are important, and I will ignore the ones which are not important, and you are free to ignore them as well. In particular, you should definitely ignore the last guy, okay? It's not really important. Okay, so let's start with, okay, so admitting a finite KG1, I will not explain. I think this is clear. So let's move to the L2-acyclicity. So we have our group is, it's a fundamental group of X, but what we really care about in this setup is that it acts on the universal covering. And the quotient is compact, right? So X tilde has a chain complex. This is the cellular, say, R cellular chain complex. So it stops somewhere, there's some Cn minus 1, and so on, and here we have the boundary maps. Now what is important is that the boundary maps, well, of course they are linear, but also we have the group action on X tilde, and the boundary maps are equivariant with respect to the group action. Okay? This is the key point. So partial is G equivariant. Okay? So in particular, this means, so what are these guys? So if you, each of them up to the action of G has a finite basis, because after all, X is finite. So these guys really are, so each Ci of X tilde is a finite dimensional 3 ZG module. Okay, so we will not really think about this chain complex as anything topological. We are going to think about it as an algebraic object. Okay, so this is now a chain complex of 3 finite dimensional ZG modules, and the partials, as I just told you, are G equivariant, so they are ZG maps. All right, so here. So we are moving into the definition of the second bullet point of property star, which is L2-acyclicity. And L2-acyclicity tells you the following. So G is L2-acyclic means precisely that if you take this chain complex C star of X tilde, these are ZG modules. So we can tensor it with some other ZG module, and we are going to tensor it with L2 of G, which is a nice ZG module. And L2-acyclic means that the homology of this guy, it's another star, I guess, is trivial. Okay? L2-acyclic means nothing else. You have this ZG chain of ZG modules, you extend scalars to L2, and now it becomes all trivial. So this is this bullet point. And the second one. Okay, now the third bullet point, and this is going to be the biggest black box in this talk. So it's about a ring DG. So whenever you have a group, you can embed it, the group ring, you can embed into a ring called DG. Now the point is that I don't want to tell you what this is, okay? It comes from von Neumann algebras, but it's really not important. I will give you the two important properties of this DG in a second, yeah? For now, what you have to know is that for any group, you can perform such an embedding, okay? This is a well-defined object, yes. Torsion free? Yeah, I probably meant reduced, but I'm going to skip that bit anyways in a second, so, okay. Okay, so now here's the thing. So G satisfies, so G which satisfies the first bullet point satisfies the Atiyah conjecture if and only if this dg is a skew field. Okay? So I should mention it's actually an open problem. You take a torsion-free group, can you embed its group ring into a skew field? Yeah, so for groups which satisfy Atiyah conjecture, this is the answer, and this mysterious object here is a skew field, and this is one of the two important properties that we need. Actually, there are three important properties, I guess. So this is the first one. Now, what's the second one? The second one is that actually, if we look at this complex of x tilde, what we did before was to tensor it with, where do I have it? Oh, here, yeah. So we tensored it with L2G, okay? But we can also tensor it. This guy is also a ZG module. So instead of tensoring with L2G, we can tensor with the skew field. Okay, so we're going to do this right now. And this is still acyclic. Okay? So we forget about L2. L2 is not important. What we did is we took this chain of ZG modules, finite dimensional ZG modules, and we extended scalars to a field. Okay? So what we are looking at now these are vector spaces. Finite dimensional vector spaces, okay? We are in the best possible setup. We have now a chain complex of finite dimensional vector spaces, except we are over a skew field, yeah? So there's a caveat. All right, so now you know, so we are going to rewrite it as dg, so let me just check the notation. Okay. So this is really a complex like this. There's dg to some k1, dg to k2, blah, blah, blah. Yeah? All right. Okay, so what can we do now? So we have a chain of vector spaces, and we know that it is acyclic, has no homology. So this means that we can break it into bits. Okay, so we are going to break it into bits. So break in bits. The point is that we can break it into a bunch of complexes which look like this. There's some Li. This comes from the partial. This is essentially the same guy as it was, except now here we have an Li as well. Okay, so you start on the left. You have dg to k1. You know that the partial is injective, so you can see this vector space as sitting inside the other vector space, and there are vector spaces so you can find an orthogonal complement. So this is what you do, okay? By taking orthogonal complements, you break this entire chain complex into a bunch of chain complexes which look exactly like this. They have only two terms with the same dimension, okay? And now the point is that this guy, I give him a name, yeah, I call it Mi, sorry. So Mi is a square invertible matrix over dg. Yeah, it's invertible. That is the key. So now I should give you some general propaganda. So what's the idea of torsion in homology? So it really comes down to the following observation. Take a matrix, a square matrix, over a field, just an honest field. What can you do with such a matrix? Well, the first invariant you want to look at is how big is the kernel of this matrix. Yeah? If the kernel is of some size, you have the dimension, that's an invariant. Now, it might happen that the kernel is trivial, meaning that your matrix is invertible. And if that's the case, you take the determinant. Okay? So the size of the kernel is the L2 Betti number, the determinant is the universal L2 torsion. This is the propaganda. And now we're going to turn the propaganda into actual mathematics, because what we are going to do is we are literally going to take the determinant of this matrix. Okay? So now here's the thing. How do you take a determinant of a matrix which is not over a field, but over a skew field? And this can be done. This is called the Dieudonné determinant, and it's simple-minded. You do Gaussian elimination until your matrix is upper triangular. You take the product of elements on the diagonal. That's it. That's the determinant. Okay, so now I told you that we are going to break this guy into bits like this. For each of them, you compute the determinant. We take the product of these determinants, and this is the universal L2 torsion of the group. Yeah, there are some minus ones, right? So there are some plus minus ones. Okay. I mean, it's well defined. I can tell you what they are, but it's all about being alternating, right? If you bit, the first bit is going to be positive, the second negative, and so on. Okay, but that's really not important. The important part is the propaganda. The propaganda is that it's just a determinant. Yeah, it's a determinant of a matrix of a skew field. That's what it is. Okay, so now the question arises: where does it live? So if you take a determinant, normally you would live over the skew field, over the field over which you are, right? Except, I mean, we know that we are non-zero, so I can take the group of units. So I kicked 0 out. But now, with the Dieudonné determinant, there's a slight problem. Namely, when you do reduction into upper triangular form, you might have accidentally swapped some rows. You don't really control that. So now, when you take a product of the guys on the diagonal, you don't really know in what order to take the product. And we are over a non-commutative field, so that makes a difference, yeah? So the answer is that you just have to quotient out the commutator, right? This is just a group, so you can do that, yeah? But now, what I wanted to tell you is that you can forget about this. Okay, we are going to treat this guy as if it was honestly living here. Yeah, this is not important for what we are going to do. Okay, so first of all, maybe I should say this is the definition. This is the definition. It's by Friedl and Lück. So what you might notice is that we talked about the action of G on x tilde, and definitely up to this point, everything a priori depends on x tilde, but here I said that this is a well-defined determinant of G, right? And the point is that here I'm using this last dot. The last dot is what allows you to pass from x tilde to G, okay? So if the Whitehead group of G is trivial, then you know that this is actually a well-defined determinant of the group, not just of the group acting on x tilde, okay? But the conjecture is that all torsion-free groups have trivial Whitehead group, so you can forget about it. Okay, so this was that. Yeah. Now, so I promised you 3 crucial facts about dg. We already saw 2. One was that it's a skew field. The second one was that we can actually replace L2 by dg in the L2 homology calculation. And here's the third fact. The third fact is that actually this can be understood as fractions, p times q inverse, where these guys live in some group ring of the free abelianized part of G. Okay, so G fab is just the free part of the integral homology. Okay, and here's K, and K is the kernel of the map from G to G fab. All right, so this is the fact I ask you to believe. We have the map from G to G fab, we have the kernel, we can apply this deconstruction to the kernel. This is the field dg. It's completely irrelevant what it is for now, okay? It really doesn't matter. We're going to see it in a second. But the point is that you can write every element here as just some bunch of guys in the free abelian part, I mean in the abelianization, with some funny coefficients, divided by another guy of that type. This is really all that we care about. Okay, so now I wanted to give you a schematic of what's happening. So first of all, we had the group G. Now we performed essentially some determinant trick, and we arrived at this universal L2-torsion. Now we're going to perform another trick, which will be called poly, and arrive at two polytopes, and then we're going to do another thing and do a norm. Okay, so I will explain all that. Okay. So where are we? We took a group satisfying our properties star. We constructed the universal torsion. It lies in dg. Yeah, we forget about this abelianization, doesn't matter. So we can write it as a fraction. Okay, this is precisely what it says here. Every element in dg can be written as a fraction of these elements. Yeah, these elements live in some group ring of G fab. Okay, so now what is an element of a group ring? Well, an element of a group ring is a finite number of group elements with non-trivial coefficients. Yeah? So in particular, to such an element, we can associate its support. Now the support lives inside, I should get rid of this. The support lives inside G fab, which is, after all, the first homology of GZ3. Okay? And this lives inside the first homology with real coefficients. Yeah. Which is nothing else but a finite dimensional vector space, right? Finite dimensional real vector space. So, if you have a bunch of points in R to the n, you can take the convex hull. This is a polytope. Okay, so I defined a polytope map, capital P, of little p to be the convex hull of support of P. Yeah, this is now a polytope. It's a polytope living inside the first real homology of the group. So this is this poly map here. We apply it to our universal L2-torsion. Which, as you remember, was some fraction. And we are going to get a formal difference of two polytopes. Okay, it doesn't matter where it lives. You can think of it as a pair of polytopes. Yeah, it's just a formal difference of two polytopes. Okay, and now we are not quite yet there, but we're almost. So now I have to explain the last guy. This is the norm map. So maybe I will need more space for this. So here's the norm. So I start with a polytope. So P is a polytope in H1G R. And now I'm going to define a map NP. NP is a map from the first cohomology to 0 infinity. Okay, what does it do? It's easy to see it on the picture. So I have to tell you what it does to a cohomology class. So first of all, we have this polytope P. Okay, this is P. Now I take a cohomology class, and I would think about this cohomology as a direction inside homology. Okay, so this is a character phi, a cohomology class. And now what I'm going to do is I'm going to project this polytope orthogonally onto phi, and I'm going to measure how thick it is with respect to this direction. And this is the N map. So formally speaking, NP of phi is the max of phi of A minus phi of B, where A and B lie in P. Now this is the correct picture to have in mind. I took a polytope, and now I measure how thick it is with respect to a given direction. That's the N map. All right. So what happened? Right. So we had the group G. We took the universal L2-torsion of the group. That's a fraction, P mod Q. We apply the polytope map. We get a difference of two polytopes. We apply the norm map, and we get a difference of two functions. Okay? This is literally a difference of two functions, which is just a function from the first cohomology of G to the reals. That's all we know at this point, yeah? This is what it is. It takes, yeah. But now here's the theorem. This is Friedl and Lück. I would say where G is the fundamental group of a free manifold. So this is a map from first cohomology to the real numbers, where we know such a map. There's the Thurston norm, and these guys are the same. Okay, so that's the magic. Yeah, we took this invariant, which is not so easy to define. We tortured it a lot. We did funny things to it. We arrived at the function, which a priori means nothing, and yet it is the Thurston norm. Okay, so this is supposed to justify that all the yoga was for a reason. Okay, that's where we are. Okay, so now we have a Thurston norm. Why is this nice? Well, because we can have a definition now, and the definition will say, okay, G satisfies star, and we define the Thurston norm to be, well, the norm of the polytope of the universal L2-torsion of the group. 1, 2, 3, I think it's correct. So this is our new definition of the Thurston norm. Yeah, works in a bigger generality. All right. So I think it's time to introduce free-by-cyclic groups. Point. Well, let me check if I didn't miss anything. Aha, okay, yeah, right. So here's a theorem. Well, it's really a combination of theorems by Linnell, Lück, and Waldhausen. And they say that if you take a free-by-cyclic group, or even more generally, if you take an ascending H and N extension, ascending of H and N extension of a free group, then G satisfies star. And so we can actually apply all of it. So I should maybe comment on this. So as I said, the last point is you can forget about it. Well, the first point is obvious what it means. L2-acyclic. So this is a beautiful result of Wolfgang Lück, that any mapping torus is L2-acyclic. Okay. So if you know that, if you have a group for which you know the Atiyah conjecture, and you take any automorphism of that group and take that bicyclic group, all of this applies, and this construction makes sense. Okay. So this defines the Thurston norm for a huge class of groups. Yeah. Any group you like that we understand well, hit it with an automorphism, you can apply this construction. Okay, but what we are interested in is free-by-cyclic groups. Well, of course, mainly because they are similar to three manifolds, and then actually our construction makes sense. So here's the first theorem I wanted to present. So this is due to Florian Funke and myself. So as we discussed, this guy is a function from first cohomology to the real numbers. That's all that we know a priori. But it turns out that for free-by-cyclic, well, ascending H and extensions for free groups, this guy is a semi-norm. Okay, for this we follow Friedl and Lück. We use their ideas really. Okay, so this Thurston norm is actually a semi-norm still, even in this setup. How much time? Okay. Right, so before I can state another theorem, we have to discuss another object, I'm afraid. The Alexander norm. So we take a finitely generated group, and to a group you can associate the Alexander polynomial. So I don't have time to tell you what it is, how you do it. You probably heard about it in context of knots. You can actually do it for finitely generated groups. And what it is element in the group ring of ZG fab. Okay, it's a well-defined object. But now, if we have an element in a group ring, we already know what to do. Yeah, I mean, what's the most obvious thing you do with an element of a group ring? You take its support, take the convex hull, and apply the norm map to it, right? I mean, of course, that's what you have to do. So the definition of the Alexander norm is precisely that. It's NP of dg. Yeah. Recall that we had our P construction we applied this P construction to an element of the group ring with some super funny coefficients in this skew field dk. Here it's z. It doesn't matter at all, right? We pass to the support. So we forget the coefficients. They are not important. Right. So this way we have a norm. This is called the Alexander norm. I think it was defined by Macmillan, this form. Or maybe not. Maybe it was defined by Alexander himself. But anyways, here's the theorem of Macmillan. Theorem. So M is a 3-manifold. With a Betti number, at least 2, the first Betti number. This is the usual Betti number. Then what happens? Well, we know that the Alexander norm is the lower bound for the Thurston norm. And this is a really good result for the following reason. The Alexander norm, I mean, I didn't tell you how the Alexander polynomial is defined, but it's easy to compute. You give me an automorphism of the 3 group, and I can give you the Alexander polynomial. It's really easy. Whereas the Thurston norm is hard to compute, both in its topological guise and through our universal L2-torsion. Okay, so this is a useful thing because this is actually easy to compute. And secondly, Macmillan proved that if phi is phi bet, phi is a character, then these norms actually coincide. Okay, it's a result of Dunfield that they actually do not coincide in general. It's not the same norm, but it is for phi bet characters. All right, and now here's the main theorem. So this is the theorem of Florian and myself. And we prove that if we take an ascending H&N extension of Fn, where, okay, here's the n is 2, or f is unipotent polynomially growing automorphism, and the Betti number of G is at least 2, so this is just the same assumption as here, then the Alexander norm is a lower bound for the Thurston norm. Yeah, and there's a fibering thing. If phi is phi bet, okay, so what does it mean? So phi bet in this setup means that, so f is a character going to z. It has a kernel. If this kernel is finitely generated, then we call phi phi bet. This really corresponds to fibering in the 3 manifolds. If it's phi bet, then actually the equality is still there. Yeah. And there is a third point. The third point is that the universal L2-torsion of G controls the Bieri-Neumann-Strebel invariants. So I did not have the time to define them, so I cannot really, I can give you a, well, I will tell you a little bit about this right now. Yes? No, it's really equal. I'm sorry, but we tried. So, but I should defend this maybe. So, why is it only n equals 2? So, there is another result that I didn't mention, which is similar in similar vein, and it's about two generator, one relator groups. And now, why is it so easy to work with this for two generator, one relator groups? Because the matrices you get, so you have to compute the determinant of a matrix, right? And these matrices in that setup are 1 by 1 matrices. And I guess we all agree that determinants of 1 by 1 matrices are not so hard. Now, the N2 means that we had to deal with 2 by 2 matrices, and that was significantly harder, and we do not know how to deal with general matrices. Yeah? So it's really an algebra problem. If we get a better understanding of these determinants for larger matrices, this will grow. But it is really 2 for now. Mm-hmm. Yeah.
What about the ball? Do you know if it's polygonal?
Do we know if it's a polygonal ball? Yeah, it is. Yeah. So this is actually. It's like a dual polytope to this polytope. So because we get the norm from a polytope, we essentially know exactly what unipole is. Yeah. Okay, I think I have still 2 minutes, so I wanted to talk about BNS invariance a little bit. So I will not define BNS invariance. I will tell you how the control looks like. Okay, so let's just take F, which is a UPG. So UPG just means, just think of polynomially growing, okay? Say any polynomially growing automorphism of Fn. Then we actually know what this, the polytope of the universal L2-torsion of Fn times F. We know what it looks like. It's typically a difference of 2 polytopes, but in our case, this is just a single polytope, and it's in fact a parallelotope. So something like that. And now the control of the BNS invariant is that if we have, let's say that we have one character, phi. To this phi, I can associate its minimum on this polytope, meaning all the points which are minimal when you evaluate them under phi. Okay, so generically, this is one vertex. When this guy starts wiggling, sometimes you'll get an entire edge or entire face, these sort of things. And now this control of BNS invariant that is mentioned in the last bullet point means that if you take a phi and another direction psi, but you know that the minimal set of this psi is the same as the minimal set of phi, then phi lies in the BNS if and only if psi does lie in the BNS. Okay, so this means that generically speaking, so we know that the BNS invariant, which is a subset of the unit sphere in the homology, is an open set, but we don't know that its complement is open. It's not, right? But this tells you that in this setup, generically, the complement is also open. You get transitions between BNS and non-BNS only when the minimal set of your direction changes its shape. Okay, yeah, thank you.
Thank you very much for an interesting talk. Are there any questions?
So you wrote down this theorem that this universal L2-torsion gives you the first norm, and then you took this as a definition if you have an abstract group G.
Right.
So if this abstract group G is the fundamental group of, say, an spherical manifold, then the Thurston norm in 3 dimension can be expressed by the Gromov norm of the dual class by a theorem of Gabay. So you could somehow formulate the left-hand side saying this is the Gromov norm of the dual in the homology of degree n-1, n is the dimension of the manifold, and then you could ask if there is equality.
Okay.
I don't know, is this a reasonable...
That sounds very reasonable, but I have never thought about it, so we can talk about it later. It sounds, yeah. I don't know.
So does this imply that the number of components of the BNS invariant is finite?
Yeah, it does. It does. Yeah, it's. I mean, there's this conjecture of Friedl that BNS invariants for some groups should be exactly coming from polytopes, and this is precisely the situation. Yeah.
More questions? Comments? Okay, then let's thank David again.